if A is equal to set 1 comma 2 comma 4 and B is equal to set 2 comma 4 comma 5 and set C is equal to 2 comma 5, then write A minus C cross B minus C. So let's find first A minus C, that is a set 1 comma 2 comma 4 minus 2 comma 5. Since we know the definition of the difference of two sets A minus B, x such that x belongs to A and x does not belongs to B, means we need to consider the elements which are there in A only, so which are not containing in the set B. So here in A minus C we need to consider the elements which are there in only A, which are not there in C. So first let us identify what are the common elements in both. Only 2 is the common element. Then other than 2, so 2 must be eliminated. So other than 2 we can take out the elements as 1 and 4. So 1 comma 4 can be taken as A minus C, and similarly B minus C can be written as 2 comma 4 comma 5 minus, and C is nothing but 2 comma 5. So here we can observe that there are two elements common, 2 is common and 5 is also common. So the only element in B which is not there in C is nothing but 4. So we can write a set with only 4 elements. Then A minus C cross B minus C is equal to a set with 1 comma 4 cross 4. So which can be taken the ordered pairs, since A cross B is equal to, so we'll consider the ordered pairs A comma B such that the first element belongs to the first set and second element must belongs to the second set. So we can take the ordered pairs, the first element 1 comma second element 4, and again we can consider the first element from the first set 4 and the second element from the second set. So only these are the two ordered pairs which are possible in A minus C cross B minus C. Okay, thank you. If n of A is equal to 3, n of B is equal to 4, then write n of A cross B. So here two sets are given whose number of elements in a set A, n of A is equal to 3, and the number of elements in a set B is equal to 4. And since we know that number of elements in A cross B is equal to, in Cartesian product, the number of elements in A cross B, that is n of A into number of elements in B. And if there are three sets can be taken, number of elements in A cross B cross C can be taken as number of elements in A into number of elements in B into number of elements in C. We can write like this. So, or we can also write n of A cross B cross C can be taken as number of elements in A into number of elements in B cross C. Or we can write number of elements in A into number of elements in B into number of elements in C. So this is how also we can generate the formula. And so now, as per the given problem, the number of elements in A cross B can be written directly as n of A into n of A into n of B. Or we can also write it like n of A into n of A cross B. Or we can write n of A into, again by using the number of elements in Cartesian products, we can add n of A into n of B. So in both the case you will be getting number of elements in A is 3, number of elements is A 3, number of elements in B is 4. So 3 3s are 9, 9 4s are 36. Here also you will get the same answer, 36. Okay, right, thank you. If R is a relation defined on the set Z of integers by the rule x comma y belongs to R, if and only if x square plus y square is equal to 9, then write domain of R. So given here the relation R is equal to x comma y such that x square plus y square is equal to 9, where x and y are integers. And the sum is equal to 9 means one can be odd and even, because odd plus odd, the sum of two odd numbers will become an even, and sum of two even numbers also will become an even number. So to get the odd number, only the possibility can be taken odd and even. Odd and even can be odd. So x square plus y square is equal to 9. Like suppose if x is equal to 0, so that y square is equal to 9. And since x and y are integers, so we can write y is equal to square root of 9, or we can write plus or minus 3. So when x is 0, y is equal to plus or minus 3 possibility. It's an odd numbers. And when x is equal to 3, so we'll have y square is equal to 0. So which implies y is equal to 0. Or even when x is equal to minus 3 also the same, y square is equal to 0, which implies y is equal to 0. And only these are the possibilities we can come across. So we can write the relation R is equal to x is 0, 0 comma plus 3, and 0 comma minus 3 is one ordered pair, two ordered pairs. And when x is equal to 3, y 0, and when x is equal to minus 3, y 0. So these are the four different possibilities we can come across this problem. So the domain can be taken. Domain is the element to be taken x such that for x comma y belongs to the relation R. The first element we can consider. So that is 0 and minus 3 and plus 3. So only these are the three elements, minus 3 comma 0 comma 3 we can take. This is the answer. Okay, thank you. If R is equal to a set with ordered pairs x comma y, where x and y are integers, and x square plus y square is less than or equals to 4, is a relation defined on the set Z of integers, then write the domain of R. R is equal to a set with ordered pairs x comma y, where x and y are integers, and x square plus y square is less than or equals to 4. So integers which satisfy this condition, let us check. If x is equal to 0, implies y square is less than or equals to 4, that is y square minus 4 is less than or equals to 0, or we can write y plus 2 into y minus 2 is less than or equals to 0. That's y lies between minus 2 and plus 2. And since y belongs to integer, so we can consider the values of y can be taken 0, or plus 2 and minus 2, plus or minus 2 and plus or minus 1. So we will get the ordered pairs. And similarly for y is equal to 0, so we will get that x square is less than or equals to 4. The possible values of x can be taken 0, plus or minus 1 and plus or minus 2. And anyhow I required only the question of domain. Domain means the first element, that is x. So we can consider only these values can be the domain. So x is equal to 0, plus or minus 1, plus or minus 2 can be considered. Before that, let us write the relation also. R is equal to, so if x is equal to 0, so we can take y values can be taken 0 comma 0 and 0 comma 1 and 0 comma minus 1 and 0 comma 2 and 0 comma minus 2. And again, if suppose y is equal to 0, so we can write x is 0 comma 0 and plus 1 comma 0 we can write, and minus 1 comma 0 we can write, and 2 comma 0 we can write, and minus 2 comma 0. So only these are the possibilities which satisfies the relation x square plus y square less than or equals to 4, and hence the domain can be taken. Domain of R can be taken only the first element of each ordered pair. So those are 0, plus 1 and minus 1, and plus 2 and minus 2. So minus 1 comma plus 1 comma minus 2 comma plus 2. So this is the answer. Okay, thank you. If R is a relation from set A is equal to 11, 12, 13 to set B is equal to 8, 10, 12, defined by y is equal to x minus 3, then write R inverse. So given relation R is equal to x comma y such that y is equal to x minus 3, where x belongs to set A and y belongs to set B. So the given condition y is equal to x minus 3, or we can also write x minus y is equal to 3. If the difference between the two elements is 3, so we can select the ordered pairs like r is equal to, so if x is equal to 11, then we can select 8 such that 11 minus 8 is equal to 3, and another ordered pair we can select here 12. The difference of 12 minus 8 is 4, and 12 minus 10 is 2, and 12 minus 12 is 0, so we are not getting 3 with 12. So let us select another element 13. 13 minus 8 will get 5, and 13 minus 10 you are getting 10. 13 minus 10 you are getting 3, so we can select the ordered pair 13 comma 10, and 13 minus 12 is 1. So only the two possible ordered pairs you are getting, r is equal to 11 comma 8 and 13 comma 10. Then r inverse is equal to x comma y, so we can write y comma x such that x comma y belongs to r. So we'll have 8 comma 11 and 13 comma 10. So 8 comma 11 and 13 comma 10 will give the relation r inverse. Okay, thank you. Let A is equal to set 1 comma 2 comma 3 and r is equal to a comma b such that mod of a square minus b square is less than or equals to 5, and where a comma b belongs to a. So then write r as a set of ordered pairs. So we need to write in the roster form. It's given in set builder form, we have to write in roster form. And since we know that the relation will be a subset of the Cartesian product A cross A, because it is defined on the set A. So let us write first A cross A. So that's 1 comma 2 comma 3 cross product with 1 comma 2 comma 3. So total 3 into 3, 9 and 9 ordered pairs you will get in A cross A. So let's find them 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2 and 2 comma 3. Next 3 comma 1, 3 comma 2 and 3 comma 3. Now among these 9 ordered pairs, we have to select the ordered pairs which satisfies the given condition. So we can write the relation r is equal to, so 1 comma 1, 1 square minus 1, that's satisfying. So 1 comma 1 is satisfying the condition mod of a square minus b square less than or equals to 5, and 1 comma 2, if I can see 1 1 square 1, 1 minus 4, it's minus 3, mod of minus 3, that is 3. 1 comma 2 also satisfies, and 1 comma 3, 1 minus 9 minus 8, that's 8 is less than or equals to 5. So 1 comma 3 is not satisfying, and 2 comma 1, 2 to the 4 minus 1, 3, it is satisfying. 2 comma 1 and 2 comma 2, that's a 4 minus 4, it's a 0, so 2 comma 2 satisfying. And 2 comma 3 again 4 minus 9, so 2 square is 4 minus 3 square is 9, 4 minus 9 is minus 5, mod of it's satisfying 2 comma 3. And then 3 comma 1, 3 3 is a 9 minus 1, 8, it's so 3 comma 1 is not satisfying. And 3 comma 2, 9 minus 4, so 3 comma 2 also satisfies. And then 3 comma 3, 3 square 9 minus 10 0, so 3 comma 3 also satisfies. So we can just confirm here. So the relation r is equal to 1 comma 1, 1 comma 2, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 2 and 3 comma 3. So except 1 comma 3 and 3 comma 1 remaining from a cross a satisfies the relation, satisfies the condition. Okay, right, thank you. Let r is equal to x comma y, ordered pair x comma y such that x and y are integers, x comma y belongs to z, and y is equal to 2x minus 4, the relation given. And if a comma 2 and 4 comma b square belongs to r, so a comma minus 2 belongs to r, so which implies that, so we can substitute x is equal to a and y is equal to -2. So it satisfies the condition, that's -2 is equal to 2 into a minus 4. So that is -2 is equal to 2a minus 4, or we can write 2a is equal to 4 minus 2, that is 2. So a is equal to 1, and 4 comma b square also belongs to 4 comma b square belongs to the relation R, so which implies, so x is equal to 4 and y is equal to b square will satisfy the given condition. So that is b square is equal to 2 into 4 minus 4. So that is b square is equal to 2 4s are 8 minus 4, that's 4. So b is equal to square root of 4, that's plus or minus 2 you will get. So the values of a can be taken, a is equal to 1 and b is equal to plus or minus 2. Okay, right, thank you. If R is equal to 2 comma 1, 4 comma 7 and 1 comma minus 2 and so on are the terms of a relation, then write the linear relation between the components of the ordered pairs of the relation. Since the question is about the linear relation, so let us consider y is equal to ax plus b be the required linear, so be the linear relation in R. So 2 comma 1 belongs to R implies, so y is equal to 1 and x is equal to 2, so we can substitute 1 is equal to 2 into a plus b, and also we can take one more ordered pair. 4 comma 7 belongs to R, so which implies that 7 is equal to 4 into a, so we can write 4 into a plus b. On solving these both equations, so subtracting 1 minus 7 it's minus 6 and 2a minus 4 that's minus 2a, and b get cancelled, so we got it 2a is equal to 6 or a is equal to 3, and substitute a is equal to 3 in any one of the equation. So let us substitute in the first equation. So 1 is equal to 2 into 3 plus b, so b is equal to 1 minus 6, it's a minus 5. So we got a is equal to 3 and b is equal to minus 5. So therefore the linear equation y is equal to ax, that is 3 into x plus b, that's minus 5. So we can consider the relation y is equal to 3x minus 5. Okay, so which also satisfies the last point 1 comma minus 2, so that's verified. 1 minus 2 is equal to 3 into 1 minus 5, so we can check that minus 3 is equal to 3 minus 5 minus 2, it is satisfying. So we can conclude y is equal to 3x minus 5 is the answer. Okay, thank you. If a is equal to 1 comma 3 comma 5 and b is equal to 2 comma 4, list the elements of R if R is equal to x comma y such that x comma y belongs to a, such that x comma y belongs to, sorry, this is x comma y belongs to a cross b, we can write, and x is greater than y, or else we can say R is equal to x comma y such that x belongs to a and y belongs to b and x is greater than y, and it is a subset of a cross b. So let us write a cross b first. So set 1 comma 3 comma 5 cross product with 2 comma 4, so we will get an ordered pairs 1 comma 2, 1 comma 4, 3 comma 2 and 3 comma 4, 5 comma 2 and 5 comma 4. So among these ordered pairs, so we can select the ordered pair such that the first coordinate is greater than the second coordinate. So we can select 3 comma 2, so 3 is greater than 2, and 5 comma 2, 5 is greater than 2, and 5 comma 4, so we can take 5 comma 5 is greater than 4. So the relation R is equal to 3 comma 2, 5 comma 2, and 5 comma 4. Okay, right, thank you. If R is equal to a set with ordered pairs x comma y such that x comma y belongs to W, its whole numbers, and 2x plus y is equal to 8. Then write the domain and range of R. R is equal to x comma y such that x comma y belongs to whole numbers and 2x plus y is equal to 8. So since the relation is given 2x plus y is equal to 8 or y is equal to 8 minus 2x, and since x and y are whole numbers, x comma y are whole numbers, so let's start taking x is equal to 0, so which implies y is equal to 8 minus 2 into 0, that is 8, and for x is equal to 1, so y is equal to 8 minus 2 into 1, 8 minus 2 it is 6, and for x is equal to 2, so y is equal to 8 minus 2 into 2, 8 minus 4 is 4, and for x is equal to 3, so y is equal to 8 minus 2 3s are 6, that's 2, and for x is equal to 4, so we have y is equal to 8 minus 2 into 4, it's a 0, and for x is equal to 5, y is equal to 8 minus 2 into 5, which is equal to minus 2, which is not a whole number, so we cannot take x is equal to 5. So only up to x is equal to 4 we can consider, and so the relation domain is nothing but the first coordinate, that is x. So we can consider the values of x can be taken 0, 1, 2, 3 and 4, and the range, so say you can take the second coordinate, y coordinate, that is 0, 2, 4, 6 and 8. So the domain and range are these values. Okay, thank you. Let A and B be two sets such that n of A is equal to 3, that is number of elements in set A is equal to 3 and number of elements in set B is equal to 2. If x comma 1, y comma 2, z comma 1, the ordered pairs are in A cross B, so x comma 1, y comma 2 and z comma 1, they belongs to the Cartesian product of A and B. So definitely the first element of each ordered pair must belong to the set A, and second element of each ordered pair belongs to the set B. So we can write the elements of A can be taken x comma y comma z, and also it is given that number of elements in set A is 3, so these are only the possibilities. So A is equal to x comma y comma z, the first element, and coming to the second element we can consider in the set B, and also second set is containing two elements, and we can find here one is one element and the next element 2, and again 1 is one more, so we'll write only 1 and 2, so it is also satisfying since n of A is equal to 3 here and n of B is equal to 2 satisfies the cardinality, and hence we can conclude that A is equal to x comma y comma z and B is equal to 1 comma 2. Okay, right, thank you. Let A is equal to a set given 1 comma 2 comma 3 comma 5 and B is equal to set with 4 comma 6 comma 9, and R be a relation from A to B defined by R is equal to x comma y such that x minus y is odd. It is an odd number. Write R in the roster form. Since we know that the difference of two numbers is odd only when one of the number is odd and one is even. That means odd minus odd will become even, or even minus even also will become an even number, and odd minus even or even minus odd. With the difference of even and odd only will get odd numbers. And since we required only odd numbers, so we will consider these cases odd and even. That is, from the first set if we can consider odd number, and next set we need to think about even number. So the relation R will contain 1 in the first set, and we need to see the even numbers. So 1 comma 4, so that 1 minus 4 is a minus 3, it's a negative odd, and comma 1 comma 6 we can consider, and 1 comma 9 we cannot take, both are odd numbers, we'll get an even number. So with 1 only the two possibilities, and coming to 2, so when set A element is even, so we need to find the odd number from the set B. So 2 comma 9 is only one odd number, 9, so 2 comma 9 is one possibility. And now 3 with 3 is an odd number from the set A, so we need to calculate, we need to find the even number from set B. So we can take 3 comma 4, and we can take 3 comma 6 also. And coming to the next one, 5 is an odd number in the set A, so we must take the even number from the set B. So we can consider 5 comma 4 and 5 comma 6. So we can see that each and every ordered pair here, their difference x minus y is an odd number, whether it is a negative odd number or positive odd number. So we are getting an odd. So we can conclude that this is our relation which is in roster form. Okay, thank you.